How do mathematicians measure the size of vectors in infinite dimensional spaces? And why are Banach spaces one of the most important structures in modern analysis, quantum mechanics, and differential equations? Standard vector spaces give us a baseline algebra. They define exactly how to add two vectors together onto the vector space itself. In mathematics, this geometric structure is called the norm. The formal pursuit of measuring abstract spaces began in 1906, when Maurice Furché introduced metric spaces to calculate the distance between arbitrary elements. But functional analysis required a stronger structure, one that inherently respected vector algebra. In the early 1920s, mathematicians like Norbert Wiener and Stefan Banach codified exactly that. They defined the norm as a mathematical function that takes any abstract vector and assigns it a strictly real, positive number representing its length. It is written using double vertical bars bounding the vector. Applying a valid norm to a vector space transforms it from a purely algebraic void into a measurable geometric landscape. For a function to qualify as a norm, it must satisfy 4 strict axioms. Axiom 1 is positivity. The length of any vector must be greater than or equal to 0. You cannot have a negative length. Axiom 2 is definiteness. The only vector with a length of exactly 0 is the 0 vector itself. If a vector has any magnitude whatsoever, its norm is strictly positive. Axiom 3 is homogeneity. If you multiply a vector by a constant, you scale its overall length by the absolute value of that constant. Tripling the vector triples its norm. Axiom 4 is the triangle inequality. The shortest distance between 2 points is a straight line. Therefore, the length of 2 vectors added together can never exceed the sum of their individual lengths. Any mathematical function that satisfies these 4 specific rules immediately upgrades a standard vector space into a normed space. Every norm automatically generates a distance metric. You simply calculate the norm of the difference between 2 vectors to find the exact distance separating them. This raises a structural question. Does every metric space qualify as a norm space? The answer is no. A metric created by a norm must possess translation invariance. This means shifting 2 points by the exact same vector will never change the distance between them. In Erwin Kreyszig's text, he highlights the space Cis, a metric space of sequences. It contains a perfectly valid distance formula, but it fails translation invariance and cannot scale linearly. Because of this failure, that metric cannot be derived from a norm. A norm is a much tighter mathematical restriction because it forces the spatial geometry to perfectly obey the underlying algebra. In infinite dimensional spaces, size is entirely relative. The physical shape of the space changes depending on which mathematical norm you apply. Consider standard Euclidean space. Here, the norm is calculated by taking the square root of the sum of the squared components. This animated diagram shows the unit sphere, the boundary containing every single coordinate point where the calculated length is exactly equal to 1. Under the Euclidean norm, also known as L2, this creates a perfect circle. But if we apply the L1 norm, distance is measured by summing the absolute values of the coordinates. The geometry warps. The unit sphere is now a diamond. If we use the supremum norm, or L infinity, the size of a vector is simply its largest absolute component. The unit sphere expands into a perfect square. Each norm defines a completely different physical reality. To understand a space, you must know exactly which norm dictates its boundaries. Norms are not restricted to coordinate vectors. They can be applied to entire functions, treating a complex continuous curve as a single measurable point in a massive function space. Take the space of continuous functions, CAB. If we apply the maximum norm, the distance between 2 functions is simply the largest vertical gap between their curves. Alternatively, we could apply the L2 norm. Here, distance is measured by calculating the total integrated area under the squared difference of the curves. Look at this graph displaying a sequence of continuous functions. With each iteration, the curve gets aggressively steeper and sharper right in the middle. This forms a Cauchy sequence. The functions are getting closer and closer to each other. Under the L2 norm, the distance between these steepening curves shrinks toward 0. the sequence is technically converging to a final limit. But the final limit of this specific sequence is a discontinuous step function, and a discontinuous function is strictly forbidden from existing inside our space of continuous functions. The sequence converged, but it converged to a point entirely outside the allowed universe. The destination simply didn't exist. Attempting calculus in a space with missing limits is like trying to cross a bridge with holes in it. Eventually, your solutions will fall through the floor. This flaw introduces the topological concept of completeness. A space is complete if it carries an absolute guarantee that every single Cauchy sequence converges to a limit that actually lives inside the space itself. When a normed space is mathematically complete, it earns a new title, a Banach space. The space of continuous functions under the maximum norm is a Banach space, but as we saw, under the L2 norm, it is dangerously incomplete. A Banach space patches the analytical holes. It creates a flawless enclosed arena where limits are guaranteed to exist and equations can be solved safely. Norms give vectors concrete length. Normed spaces provide rules to measure distance. Completeness ensures no holes. Banach spaces combine these to solve advanced calculus. Without the guaranteed structures of Banach spaces, proving the existence of solutions in quantum mechanics, optimization, and differential equations would be mathematically impossible. If you want complete explanations of books like Kreyszig, Rudin, functional analysis, linear algebra, real analysis, and topology, then don't forget to like, subscribe, and share this video. Comment below which theorem, proof, or chapter you want explained next. Thanks for watching, and see you in the next video.